I wanted to work through an example of the calculation of the torque on a current carrying loop that is immersed in a uniform magnetic field. So this is an example of what we call the electrical motor, in which a current carrying loop is immersed in a magnetic field to create rotational motion. So we're actually going to calculate that torque on that loop in that field. The question says that there's a loop with a single turn that's a circular loop with a radius 32 centimeters. And that loop is carrying a current of 17 milliamps. So that's all the details on the loop. And then we're told that the loop is immersed in a uniform magnetic field. The strength of the field is 0.8 Teslas, and the field is orientated so it's parallel to the loop's cross section, parallel to the loop's surface. So with that information, we're going to calculate the torque. I'm going to do it in two steps. The first thing I'll do is actually calculate the magnetic moment of the current carrying loop. That's a property of the loop itself, a characteristic of the loop itself. And then once we got the magnetic moment, we'll calculate the torque by imagining that magnetic moment in the 0.8 Tesla field and how that magnetic moment is orientated in that 0.8 Tesla field. Before I do any of that, though, I want to make a quick sketch. So we want to draw the situation in this problem. So I've got a uniform magnetic field. So here's a uniform magnetic field, and its strength is 0.8 Teslas. We've got a wire loop in that magnetic field. Now, what I'm going to do is draw the wire loop as if I'm looking down on its surface. So here it is. And what I'm seeing in this picture is the top arm of the loop. Below that would be the bottom arm of the loop. And over here on the left is the left side of the loop. Over here on the right is the right side of the loop. Let me add a few things to describe that loop, if I can do that. Let's imagine that the current is flowing up the left arm and then down the right arm. So I'm indicating that. Let's imagine that the loop is able to rotate around its center, and it will be rotated around its center here by the fact that there's a torque acting on the loop. The torque arises from a force exerted on the left arm and a force exerted on the right arm. And those forces tend to turn this loop in a clockwise direction by creating a torque about the center of the loop. So that's a picture of what's going on for the loop. The area of the loop is pi r squared, and we know the radius of the loop. The current in the loop is 17 milliamps. And that's enough information for us to calculate with the number of turns of the loop, which is just one, the magnetic moment of the loop. And so I'm going to go on and calculate that magnetic moment and then calculate the torque. So magnetic moment, let's start with that. Again, this is a property of the loop. It has this magnetic moment, whether it's in a magnetic field or not. it has this magnetic moment no matter what the orientation of the magnetic field is. It's just a property of the size of the loop, the turns of the loop, and the current in the loop. It's NIA. So uppercase N is the number of turns. That's just one here. Uppercase I, that's the current in the loop. It's 17 times 10 to the minus 3 amps. And A is the area of the loop. It's pi times the square of the radius, and the radius was 0.32 meters. And if I plug all those numbers into my calculator, I've already done it, 5.5 times 10 to the minus 3, and the units of that are amps meters squared. So it's a product of a current in amps times an area in meters squared. So it's amps meters squared. Now let's calculate the torque on the loop. So the torque really just depends on the magnetic moment, the magnetic field. It depends on the size of the magnetic moment, the size of the magnetic field, and the orientation between those two vectors. So let me go back to the diagram and just make sure we understand that orientation. So the magnetic field here, which is one of the two vectors, is from left to right. The area and also the magnetic moment are also vectors, and they're perpendicular to the face of the loop, and that's this vector here. So if you were to picture the area vector, picture the magnetic moment, picture the magnetic moment vector, it would be a vector that is 90 degrees, right angles, perpendicular to the loop's face. That means that there's 90 degrees between the direction of the field and the direction of the magnetic moment in this particular geometry. So the magnetic torque that arises equals mu, the magnetic moment, times B, the magnetic field, times the sine of the angle theta between those two vectors. In this case, we calculated our magnetic moment is 5.5 times 10 to the minus 3, and that units were amps meter squared. We've been given the magnetic field. That was 0.8 Tesla. And we've been given the orientation. There's 90 degrees between the direction of the magnetic field and the direction of the magnetic moment. So multiplying these quantities together, I've already done that. I got the torque, which was 4.3 times 10 to the minus 3, and the units of torque are Newton meters. And so that's the answer to this question. Just a couple of final points about this question. So in calculating the torque and in calculating the magnetic moment, we use the area of the loop. But it doesn't matter whether it's a square loop, a circular loop, or some other shape of loop. All that counts is the area. In calculating the magnetic torque, we needed the orientation of the loop in the magnetic field. So we got a maximal value for the torque because our magnetic moment was at 90 degrees to the magnetic field. If we had arranged our loop in the field so that the magnetic moment was in the direction of the magnetic field, or also opposite the direction of the magnetic field, we would have got a minimal torque on the loop. We would actually got zero torque on the loop. So when you put a loop, current carrying loop in a magnetic field, the torque depends on the orientation in the field. There's a maximum value, which is just simply mu b, and there's a minimum value, which is 0. And so you have to think about the orientation.